Hello friends. So today we are going to discuss few questions, and the questions are from the year 1983, and from 1983 we are having three questions. Then it is from 1984. From 1984 we have two questions, and it is finally from the year 1985, and from this also we have three questions. So in totality we are having 8 questions. Okay, so first question, it was asked in the year 1985, and it states that a beam of light consisting of two wavelengths 6500 angstrom and 5200 angstrom is used to obtain interference fringe in a Young's double slit experiment. The distance between the slits is 2 mm, and the distance between the plane of the slits and the screen is 120 centimeter. So based on this description we have two questions. Part A asks that find the distance of the third bright fringe on the screen from the central maxima for a wavelength of 6500 angstrom. And part B, what is the least distance from the central maxima where the bright fringe due to both wavelengths coincide. So first of all, we are going to solve for the part A. And part A, we have to find out the distance of the third fringe for the wavelength of 6500 angstrom. Distance of third fringe for wavelength, that is our lambda, is 6500 angstrom. Okay, so this basically means it is our for 6.5 into 10 to the power minus 7 meters. And we directly know the formula for the fringe position. So we can write that position of the mth bright fringe the position of mth bright fringe, and it is given as y of m is equal to m lambda L divided by small d, and this y of m is the distance from the central maxima. Y of m, it is the distance from central maxima, and m is the order of the fringe, lambda is the wavelength, and L is the distance to the screen. Sometimes this in place of L, sometimes capital D is also written. So you can say L is the distance to the screen. And small d is the distance between the slits. Between the slits. So we have to find out for the third branch fringe. So substituting all the values, we get this as y of 3 is equal to 3 into 6.5 into 10 is power minus 7, and it is our 1.2 meters divided by 2 into 10 is power minus 3 meters, and this will be giving us an approximation of 1.17 centimeters. Now we come to the part B, and it says that find the least distance from the central maxima where the bright fringe is going to coincide. So we have to find out the least distance from central maxima where bright fringe coincides. It means condition for coincidence for both the wavelengths. So we have two wavelengths, let us call that lambda 1 and lambda 2. So we can just use directly the formula. We can say that condition for coincidence and for bright fringes from both wavelengths to coincide. And we can write it as m1 lambda 1, and the length of that, we can say distance of the screen from the slits in the both the cases will be same. So ultimately it is going to cancel out. So this will be by L divided by D, and this also comes as m2 lambda 2 and divided by D and multiply by L. Here M, L and this 2 cancels out. So this gives us that m1 lambda 1 is equal to m2 lambda 2. And we can simply find the ratio. We get our m1 upon m2 is equal to lambda 2 upon lambda 1. So this gives us 5.2 into 10 to the power minus 7 and 6.5 into 10 to the power minus 7, and this gives us close to 4 upon 5. And from here we can say that m1 is equal to 4 times k and m2 is our 5 times k, and this k is any integer. And it is said that we have to find the least distance. Okay. So it means the value of k should be the smallest integer. Okay. So we can say that for least distance k should be equal to 1, and this gives us that our m1 is equal to 4 and our m2 is equal to 5. Now we can easily calculate the position of the coinciding fringe. Position of coinciding fringe can write that our y will be equal to m1 lambda 1 d multiplied by L, and we substitute the value, we get this as 4 multiplied by 6.5 into 10 to the power minus 7 and into 1.2, and this will be 2 into 10 to the power minus 3, and this we can say that our y will be approximately equal to 1.872 centimeters. Okay, so this is the position for the coincidence. And anything else is asked? No. Okay, so this completes the both A and B part. We come to the next question. This question was asked in the year 1985, and it states that a convex lens A of focal length 20 centimeter and a concave lens B of focal length 5 centimeter are kept along the same axis with a distance d between them. If a parallel beam of light falling on A leaves B as a parallel beam, then the d is equal to. So it means we have a combination of the convex and concave lens, and they are placed in such a way that the parallel beam falling on A should be leaving from B as a parallel beam. So we have to satisfy this condition. So therefore we can draw a rough approximate diagram. So this is our first lens, and this is the principal axis, and we have a second lens, and we have a parallel beam of light. This is our A and this is our B. So parallel beam of light that will be falling on A, it will be try to converge slightly like this, and after you can say passing through lens B, it should be once again going out as a parallel. So this is the given condition which is to be satisfied, and under this condition we have to find out what will be the distance between the these two lenses, and it is said that the focal length of A is 20 centimeter. So we can, if we extend this, it will be giving a virtual image somewhere here, and this will be our 20 centimeter, and the concave B focal length 5 centimeter. Okay, so we are going to have a distance of 20 centimeter for A. This will be over 20 centimeter, and for B this will be over 5 centimeter, because for B this virtual image is going to act as a object. And this is the basic diagram. So the parallel is the input and the parallel is the output. That is the main requirement. So we are given the focal length of convex lens, that is our A, focal length of convex lens, which is our A, and we can say that is our f of A is our 20 centimeter, and we are also given the focal length of concave lens, that is our B, and this will be our minus of 5 centimeters. Okay. And we have to make sure that the parallel beam remains parallel. This is the most important condition which is to be satisfied. Okay, so we have to say that for parallel beam to remain parallel, the second focal point of the lens must coincide with the first focal point of the second lens. Okay, so based on this, we can say that the second focal point of first lens must coincide with first focal point of second lens. Point of second lens. So therefore, we can easily find out D. D is our so D is the distance between the two. So we have to find out this D. Sorry. So this is our D. We have to find out this part. So this we can easily use the mathematical combination. So we can say that the D will be difference in the focal length of the two, and we already know it is 20 minus of 5. This gives us 20 minus 5, so the distance D will be equal to 15 centimeters. So here the important part was only one, that we have to define how the image, or we can say ray diagram, we have to define. We only know that initial and final should be parallel, and for that condition, the second focal point, this condition has to be met. So based on this, we get our D is our 15 centimeters. So we come to the next question, and in the next question it is said that we have a 1985 question, and gives a monochromatic beam of light of wavelength 600 angstrom in vacuum enters a medium of refractive index 1.5. In the medium, its wavelength and its frequency is. So we are given that the wavelength in the vacuum is given to us, and refractive index is given. We have to find out the wavelength in the medium. So this is quite straightforward based on the formula. So we are given lambda in the vacuum, which is our 6000 angstrom. So that will be our 6000 into 10 to the power minus 10 meters, and we are also given the refractive index of the medium, refractive index of medium, and that is given as 1.5. And we know the speed of the light, we already know, and then we are going to use the same standard formula, that our refractive index, which is given n, is equal to c upon v, where is the velocity which we are supposed to find out. So v will be equal to c upon n. C is our speed of light, which is 3 into 10 to the power 8, and refractive index is about 1.5. So this gives us that the velocity is equal to 2 into 10 to the power 8 meter per second. So we found out the velocity, and frequency will be same. That is our frequency we need to find out. So we can use the formula that our frequency will be equal to c divided by lambda in the vacuum. So we have c is 10 to the power 8 and lambda is our 6000 into 10 to the power minus 10. So this gives us that the frequency will be equal to 5 into 10 to the power 14 hertz. So this is the frequency. Now we can find out the, you can say, the wavelength in the medium, because the frequency is going to remain same whether it is in vacuum or it is in the medium. So this gives us that the lambda in the medium will be equal to v upon f. Velocity we already found out is 2 into 10 to the power 8, and frequency is our 5 into 10 to the power 14. So this gives us that our lambda, wavelength in the medium will be equal to 4 into 10 to the power minus 7 meters, or we can say that the wavelength in the medium will be equal to 4000 angstrom. And frequency is going to remain same. So we can say our frequency in the medium will be our f, which was our 5 into 10 to the power 14 hertz. So frequency will be same, only the wavelength is going to change. So we come to the next question. And next question, it was asked in the year 1984, and it states that we have a plano-convex lens has a thickness of 4 cm. When placed on a horizontal table with a curved surface in contact with it, the apparent depth of the bottom-most point on the lens is found to be 3 cm. If the lens is inverted such that plane face is in the contact with the table, the apparent depth of the center of the plane face is found to be 25 by 8 centimeters. Find the focal length of the lens. Assume the thickness is to be negligible while finding its focal length. So we have a plano-convex lens. So one side will be plane, other side will be the convex lens, and it has two conditions. First, curved surface is placed on the is in contact with the table and apparent depth is given. In the second case, it is given that the plane surface is now in contact with the table, and in that case also we have the apparent depth. So we can divide, or we can say draw the figure for both the cases. So in the first part, we are given that the curved surface is in contact with the table. So let us suppose this is our curved surface and that is in contact with the table, and something like this. And let me redraw it. It looks like it's falling out. So we have this as a curved table, curved lens, and we are given that the apparent, so let us suppose this is our normal, and the light from here, that is bottom, will be traveling this direction and bending somewhere here, and if this is the directly vertical, and because of this apparent, it is saying, we are going to say this is the image is somewhere here. And when it is the plane is surface is in contact with the table, so this is our plane surface, and once again we are going to have a normal. So let us draw the normal, which will be coming something like this, and it is says at the center of the this plane. Let us suppose this is the center of the plane, and this will be the vertical light, and our ray of light will be traveling and bending something like this. And once again, because of this apparent depth, we can say it will be matching somewhere here, and let us suppose this is our I2. This is the cases, case 1 and case 2. So let us, we are given a plano-convex lens. So basically means that one surface is a plane, so it means its radius of curvature for that surface, suppose that is R1, will be infinity, and the other one is convex, radius of curvature, let us suppose is our R. Okay. So we have two scenarios, and let us do it one by one. So we are given that we have a plano-convex lens, and its refractive index is given as mu. It's given a mu. It's not given. Let us assume that is mu. And second, so one of the surface will be plane. So we can say one plane surface. Because of this, the radius of curvature that is our R1 should be equal to infinity, and the other is our convex surface, and the radius of curvature is our R. Sign we can decide later on based on the orientation. And we are also given that the thickness of the object is given as 4 centimeter. Okay. And here let me mark this point. This is our A, and this is our O, and here also we have our A and point O, and this is the vertical. So therefore we are given that the object distance for the first case, let us suppose that is our U1, which is our AO, will be equal to -4 centimeter, and next is our image distance. Image distance is our V1, which is our AI1, that will be equal to our 3 centimeter, and this is for, you can say, first case. First case, that is figure is our A. Then once again we come to our second case. So we have our image distance let us suppose that is our V, and we consider that will be our AI2, that will be equal to minus 25 by 8. And refractive index, one is air and other one is lens. So we can say our refractive index, that is our mu1 will be equal to mu for our lens and mu2 will be equal for our air. So these are the basic things which are given to us. And let us find out for case A, or rather we can say figure A. Case 1, that is our figure A, curved surface contact with table. Curved surface in contact with table. So therefore, like I said, that our U1 is our minus 4 centimeter. Let me write it again. So here we have our U1, that is our AO is our minus 4, and our V1, which is our AI1, is equal to 3 centimeter, and refractive index is same, and radius of the plane surface, radius of curvature of plane surface, that is of R1 is equal to infinity. So first of all, we are going to have refraction at the plane surface. Refraction at plane surface. So we can use the formula, and that is our mu2 upon V minus mu1 upon U is equal to mu2 minus mu1 upon R. So we substitute the values, and we can, mu2 is our mu and V is our minus of 3. One second. Yeah, it has to be minus of 3 here also, and here also I missed it, minus of 3. So we have this as minus of 3. Mu2 is our air. Yeah, mu2 is our air. So this will be our 1. And this is minus mu upon minus of 4. And this gives us 1 minus mu upon infinity. So therefore, from here, we can easily write that we are going to have this as mu is equal to 4 by 3. So this we got the refractive index. Now the plane surface is in contact with the table. So we have case 2, that is our figure B, plane surface in contact with table. So once again we can write that our U, that is our AO, will be equal to minus of 4, and that is our V, in this case is our AI2, and that will become minus 25 by 8, and refractive index we just found out that is mu1, which is equal to mu is our 4 by 3, and mu2, which is our air, it will be equal to 1. And the curved surface radius of curvature, that is of r2, will be equal to minus of r. So we can say that our radius of curvature which is our r2 will be equal to minus of r. So once again we can use the formula that our mu2 upon v minus mu1 upon u is equal to mu2 minus mu1 divided by r. And rather we can say r2, and we simply substitute the values. We get this as mu2 is our 1, so we get 1 upon minus 25 by 8 minus mu1 we just found out is 4 by 3, so this is 4 by 3 upon u is our minus of 4, and this comes as 1 minus 4 by 3 divided by minus of r. So we can simplify a little bit. We get this as minus of 8 upon 25 plus, and this will be coming as 4 and 4 goes away, we will be left with 1 by 3 is equal to, and we can write this as minus 1 by 3, that is our plus 1 by 3. So we can write this as 1 upon 3 times r. So this gives us that the r will be equal to 25 centimeters. And we have to find out radius of curvature, and we have to find out actually the focal length. Okay. So we just found out radius of curvature. Now we can easily find out the focal length. So we can say focal length of plano-convex lens and we just found out that our r1 is equal to r, which is our 25 centimeter, and r2 is our for plane, that is our infinity. So we can use the formula that 1 upon f is equal to mu minus 1, and this comes 1 upon r1 minus 1 upon r2. We substitute a value, we get this as 4 by 3 minus 1 and 1 upon 25 minus 1 upon infinity, and this gives us 1 upon f will be equal to 1 upon 3 and multiply by 1 upon 25, that is our focal length will be equal to 75 centimeters. So this is the focal length which we are supposed to find out. Now we come to the next question. In the next question, which was asked in the year 1984, and it states that white light is used to illuminate two slits in the Young's double slit experiment. The separation between the slits is b and the screen is at a distance of d from the slits. At a certain point on the screen, directly in front of one of the slits, certain wavelengths are missing. Some of these missing wavelengths are. So in this case, we have to find out which of the wavelengths are missing and when they are going to, you can say, meet, or you can say converge at a point, and that point is given as directly in front of one of the slits. So we are given, indirectly we are given that where this point is going to lie. Okay, and because if we draw a rough approximate diagram, so this is our D, sorry, this is our capital D, small d. D is the screen distance. Okay, it's given D is screen distance, and it is mentioned that if this is our central point and B is the distance between the slits, so this is our B, and suppose the one of slit which is having a missing wavelength is at this point, so this is our B, so we can easily understand that this will be our B by 2. So we can write that the point is directly in front of the slit. So it means the vertical distance from the central axis, the vertical distance from central axis which is given as y will be equal to B by 2. And we have to find out basically the path difference, and that is going to help us in finding because the missing wavelength will be only because of the destructive interference. So we can say path difference which is given as delta x is equal to B multiplied by y and divided by d. We already know our y, so we substitute it here, we get this is B multiplied by B by 2 and divided by d. This gives us that the path difference of our delta x is equal to B square divided by 2d. And the condition for the missing wavelength, that is the destructive interference. We can write that condition for destructive interference and this destructive interference will be resulting in missing wavelength. And for destructive interference, the path difference, or we can say the path difference condition should be satisfied. So we can say that path difference must satisfy, and that condition is delta x is equal to m plus 1 by 2 times lambda, where this m is our 0, 1, 2 and so on. Path difference, that is our delta x, we just found out. We substitute it, we get this as b square upon 2d is equal to 1 plus m plus 1 by 2 multiplied by lambda. So this gives us that the lambda will be equal to b square, and here we have 2d m plus 1 by 2, and we can simplify it a little bit. or we can just substitute the values. So we can find out, we can take various values of m and find out the what will be the missing wavelengths. For different values of m, we get different missing wavelengths. Different missing wavelengths. So basically we are going to get, for m is equal to 0, we are going to get our lambda will be equal to b square by d. For m is equal to 1, we are going to get lambda is equal to b square by 3d. And for m is equal to 2, we are going to get lambda will be equal to b square upon 5d, and so on. Therefore, the missing wavelengths that is our lambda will be equal to b square by d, b square by 3d, b square by 5d, and so on. So the option that is our correct one is our b square by d and b square by 3d. Okay. So option number A and C are correct. Option A and C are correct. And we only have to keep in mind that the missing wavelength will be because of the destructive interference. So we come to the next question. And in this question, it is quite straightforward, and we are given that it was asked in the year 1983, and it states that a light wave of frequency 5 into 10 to the power 14 Hertz entered a medium of refractive index 1.5. In the medium, the velocity of the light wave is, we have to find out, and its wavelength. We are given the refractive index as well as frequency. So we can say our frequency, which is given as 5 into 10 to the power 14 Hertz, and we have refractive index which is given as 1.5. And we already know that the speed of light in the vacuum, that the c is 3 into 10 to the power 8 meter per second. So we can use straightforward formula, that is our v is equal to c upon n. So we have this as 3 into 10 to the power 8 and it is 1.5. So this gives us 2 into 10 to the power 8 meter per second. So this was the first part. And second part, we have to find out wavelength in the medium. So also we can use that our lambda is equal to v upon f. Velocity is, once again, we just found out, is 2 into 10 to the power 8, and this is our velocity in the medium, and this is wavelength in the medium. And frequency is going to remain same, that is 5 into 10 to the power 14. So this gives us close to 4 into 10 to the power minus 7 meters. So this question was quite straightforward, directly based on the basic formula. We come to the next question. And in this question, it was asked in the year, you can say 1983. and it states that in a Young's double slit experiment using monochromatic light, the fringe patterns shift by a certain distance on the screen when a mica sheet of refractive index 1.6, thickness 1.964 microns is introduced in the path of one of the interfering waves. The mica sheet is then removed and the distance between the slits and the screen is doubled. It is found that the distance between the successive maxima or minima now is the same as observed fringe shift upon the introduction of the mica sheet. Calculate the wavelength of the monochromatic light used in the experiment. So in this case, we have two conditions. First is the experiment is with the introduction of the mica sheet, and in the second case it is without the mica sheet. But the only condition we have to remember that the distance between successive maxima minima, it is observed to be the same upon the introduction of the mica sheet. Okay. So there is a fringe shift when the mica sheet is introduced. That fringe shift will be equal to distance between the successive maxima or minima. So this condition we have to keep in mind. And we know the basic formula, or let us first of all write the things given to us. We are given a refractive index of mica sheet, that is our mu, it is given as 1.6, and its thickness, that is our small t, is also given as 1.964 into 10 to the power minus 6 meters. And the important point which we have to keep in mind, that states that the fringe shift due to mica sheet it equals to new fringe width when the distance between the slits and screen is doubled. It is equal to new fringe width, which is nothing but distance between maxima or minima when distance between slits and screen is doubled. Slits and screen is doubled. So we have to keep mind in this particular condition. And the basic formula, that the fringe shift due to a thin sheet, we already know that formula, and we can, that is our S is equal to capital D divided by D multiplied by mu minus 1 and multiplied by T, and fringe width is beta is equal to capital D multiplied by lambda divided by small d. So first of all, let us solve it for the fringe shift, that is S, by the introduction of mica sheet. You can see that fringe shift, that is our S, due to mica sheet. And that S is given as capital D upon D, and this is mu minus 1 and times thickness, that is T. We substitute the value which are given to us, capital D and D will be same, and this will be 1.6 minus 1, and here we have 1.964 into 10 to the power minus 6. So this gives us that our shift, which is our S, is equal to capital D upon D is equal to 1.179 84 into 10 is power minus 6 meters. So this is a fringe shift. Now new distance is double that of original distance. Okay. So basically means that initially the distance between the screen is our capital D, and the distance between the slits is our small d. In the second case, the distance between the slits is now between the slit and the screen is doubled. Okay. We can say the new distance let us suppose that is our d prime, that will be equal to twice d. So in the second case, this distance is now doubled, and let us suppose that is given as d prime. So d prime will be equal to capital D, and because of this we can write that a new fringe width that is our beta prime will be equal to d prime lambda and small d. Okay, this is our small d, which is our same, and we substitute d prime, which gets 2d lambda upon small d, and it is given that the new fringe width, which is actually the distance between the maxima or minima, should be equal to slit width, the shift. So we can say that from given question we should be having that our S is equal to our beta prime. Now we substitute our S, which is our capital D upon small d, and this is our 1.1784 into 10 to the power minus 6 is equal to, we have 2d lambda upon small d, and here this d and d cancels out, and we get this our lambda is equal to 1.1784 into 10 to the power minus 6 divided by 2, and this will be approximately equal to 589.2 into 10 to the power minus 9 meters. So this was the only thing. Yeah, we have to find out only the wavelength. Now we come to the next question, and in this question it was asked in the 1983, and it states that a ray of light from a denser medium strikes a rarer medium at an angle of incident I. The reflected and refracted rays make an angle of 90 with each other. The angles of reflection and refraction are r and r prime, then the critical angle is. So we are given the figure. So this is our incident ray, and incident ray is partially reflected and partially refracted. Okay, and we are given respectively the angle as r prime and r, and between these two it is of 90 degree. So we can say this is our 90 degree, and if this is 90 degree, we can say that our r and r prime will be also equal to 90 degree. We are given that our reflected and refracted rays are 90 degree, to each other. So using this condition, we can easily say that our r plus r prime should be equal to 90, and from here we can write our r prime is equal to 90 minus r. Now we can use Snell's law. And Snell's law, it tells us that our n1 sine of r should be equal to our n2 sine of r prime. We substitute the value of our r prime, and we can write that our n1 sine of r is equal to n2. We have this as sine of 90 minus r, which gives us that n2 cos of r. And we can write this as in the form of tangent. We can say that our n1 tangent of r is equal to n2. This gives us that tangent of r is equal to n2 by n1. We have to find out the critical angle, and we know that for theta c as our critical angle, we can write that sine of theta c should be equal to n2 upon n1, and n2 upon n1 is nothing but our tangent of r. So therefore we can say that our critical angle theta c is equal to sine inverse of tangent of r, which we were supposed to find out. So we get this as sine inverse of tangent of r. That is option number A is correct. Option number A is correct. So yeah, so these were the questions which was asked in the year 1985, 1984 as well as 1983, a total of 8 questions. These complete all the questions. Thank you.